Ahoy. Thank you, Tarek, for the introduction, and thank you to Olga and Daria for inviting me over. So my talk will largely cover the work that was done within the neuroscience team at DeepMind over the last couple of years. But if there is one point that I want to take away from my talk, it's about how important it is to build good representations to reach something like artificial general intelligence. So as you might know, DeepMind is a mission-driven company. And our mission is to solve intelligence and use it to make the world a better place. These are very big words, but what does it mean in practice for researchers? Well, essentially, we want to develop a system that we can embed in a very complex world like ours, with all its messiness and craziness. And we want the system to learn and adapt and build the right kinds of reasoning blocks to perform intelligently in such an environment. But the key is we don't want to hand engineer much into the system, because we want to use the same system in a very different kind of world. For example, the world of science, where arguably the concepts used in molecular biology are very different from the concepts that you would be using in your day-to-day life. But we want to be comfortable enough in our systems that they would actually deal with this new world with its own properties and statistics and discover the right ways to reason about it to answer our questions, like how to cure cancer. So in more detail, we want our systems to work with very few supervision signals, because for the question of curing cancer, actually, we as humans don't know the answers yet. For the same reasons, we also want our systems to work with very sparse extrinsic rewards. We also want the system to learn something like a common sense for its exploration, so that when it's learning, it's not damaging itself or its environment. And finally, we want the system to be able to communicate its results back to us. So if our AI does learn how to cure cancer, we actually want to know how to do it and learn from it. So my talk will be split into 3 parts. In the first part, I will give you some motivation why I believe unsupervised representation learning is an important step to reach an agent that can work in such kind of hard situations. Then I'll describe a few algorithms that we have developed at DeepMind, which start to make first steps towards learning such representations. And finally, I will show you just one example of where good representations help us learn more robust reinforcement learning policies. But first, let's take a bird's eye view on the history of machine learning. Very roughly speaking, it can be split into 2 parts, kind of the current modern deep learning era and the time beforehand. And again, very roughly speaking, you can say that what researchers primarily did before deep learning was representation building, right? They would spend a lot of time doing feature engineering to then train their regressors. However, with the onset of modern deep learning, suddenly we can have end-to-end systems where representation learning is done implicitly. It's done somewhere within the hidden layers of the black box of the neural network. And of course, we had amazing results coming out of this kind of work. We now have image classifiers that outperform humans on the ImageNet challenge. The voice of Google is a neural network called WaveNet. But we also know that we don't have artificial general intelligence just yet. And I'm really glad that Brendan was talking before me, because I always like to bring up his paper on building machines that learn and think like humans as a very, very nice, concise way of highlighting some of the biggest issues that modern deep learning has. And like Brendan has already described this example, how the image capturing is not quite getting the true grounding of what's happening in the images. So if implicit representation learning is not getting us all the way, I want to ask a question that, is it time to revisit explicit representation learning once again? But how do we go about this? It's kind of a very vague question. And as a neuroscientist, my first instinct is always to look at the brain. And in this instance, we don't even need to look at the human brain. Even a rat brain will suffice. So a newborn rat does not receive supervision signals for each time step of its experience. It does not get the rich, highly engineered shaping rewards that we have to use to make our deep reinforcement learning agents work. However, somehow through intrinsic motivation, exploration, and just primarily unsupervised experiences with the environment, the rat is able to build a common sense understanding of how its world works to be able to survive for a few years. How does it do it? Well, the world is not just complex. It might appear infinitely complex, but it does have some structure to it, and we record and kind of, we take that structure and write it down as the formulas of physics and chemistry. But of course, again, we wouldn't expect the rat to figure out Newton's law by observing and like running around in mazes. So what these rules do give us are kind of high-level statistical regularities. And these are the regularities that the the rat brain can actually exploit. And suddenly we're talking about learning the statistical regularities of unsupervised data. And this is exactly what the field of unsupervised learning aims to do. So we're kind of converging towards learning unsupervised representations, but this is a very ill-posed question as well. How do we measure how good our representations are? And for this, I would like to think of our reinforcement learning agents, and as I just mentioned, they live and interact within a particular world. And normally in RL, there is this dual interaction that people consider, but we believe that there is a third factor. Imagine that there is some omnipresent being that has this sort of hypercube of the generative factors. And it picks a random point and says, this is going to be my world of the day. And then it presses go and generates the world, and this is the world that our agent populates. And if there is a generative structure to the world, then what we want our agent to learn is a representation that aligns with these generative factors. And this is what disentangled representation learning is about. We also want our representations to actually be useful for reinforcement learning. And a lot of literature in cognitive science says that in order to do that, the representation needs to be hierarchical and compositional. And finally, we want the agent to learn over its life rather than just learning on one dataset or one task. So let's start with the first question. Probably one of the most widely used unsupervised algorithm for disentangled representation learning currently is something called the BTVE, and it's an algorithm that we developed at DeepMind and presented at HLAI last year. It's based on the variational autoencoder framework. I will not go into too much detail, but basically you have an image that goes through an encoder network, and we get a posterior distribution, which we then sample from and use the decoder to try to reconstruct our image back. And essentially the loss function tries to optimize two objectives. One is getting a good reconstruction, and the two is kind of pushing the posterior under the unit Gaussian ball. So the VE was published by Dirk Ingma and independently at DeepMind as well a while ago. But what we added is this extra beta hyperparameter that essentially puts more weight on the KL term of the loss function. You can read the paper for derivation of this and our motivation, but what this gives us is now if we have a data that's generated by some factors, we can actually recover these factors in the latent space of the model. So each latent representation becomes axis aligned with one of the generative factors, so that if we kind of wiggle around this one latent, kind of think of it as a tuning knob on a radio, the only thing that it changes is the color of the ball. So it learned to factor out this particular generative factor and represent it. So again, if you want to understand better how this works, I would refer you to a really nice paper by Chris Burgess that's on arXiv. But so how does this compare to baselines? We trained it on a dataset of chairs, and this dataset has many different types of chairs, and they all rotate around. And the only factor that's actually labeled is the azimuth. So DCIGN, which is a semi-supervised method for disentangled representation learning from Tejas Kulkarni, is able to recover this factor really well. But it can't learn anything else because nothing else is labeled in the dataset. Very concurrently with our work, but independently, OpenAI released something called the InfoGAN. So this is an alternative unsupervised method for disentangled representation learning. And what's cool about InfoGAN is that it was able to learn the azimuth, but it also discovered another factor, which is the width of the chair. However, there was a problem. The algorithm could either pick one or the other, depending on the seed, but it never really got both. Whereas BTV found the azimuth, the width, but also we found the factor that represented the leg style, so either chair or stool. And what was really surprising to us was when we started traversing this latent, we found that the BTV imagined a new kind of chair that it has never seen before, which is an armchair with a stool leg. And this is the full set of generative factors that the BTV discovered. So we have the 3 ones I described here, plus we have a kind of back size and a few others. So now we have an unsupervised algorithm that can pull out the generative factors of the world, but it does it one data set at a time. Can we extend it to a more lifelong learning setup? And I'm actually really excited to present this work because we published it on our archive just on Tuesday, and it was the work done by Alessandro Achille, who was interning with us over Christmas. So now imagine we have a new agent and it spawns in a lab environment, and spend some time discovering about the structure of this artificial world. But then it finds a door, and that door leads outdoors, and suddenly the agent finds itself in a desert. Obviously, the data distribution has shifted quite a lot. So can we have an agent that can automatically detect the shifts in the data distribution, use its spare representation capacity to learn about the new data distribution without forgetting the old one? But also, really importantly, these two domains might look very different, but they might have some shared structure. For example, both domains have objects. So can we also share semantically relevant dimensions where relevant? So what Alessandro did was he augmented the BTV framework. So he started with the disentanglement objective. And then he added some sort of sparse coding or spike and slab flavor to it. So essentially, we add a mask on top of the latent representation to select which of the latent dimensions are actually relevant for the current environment. We then added an environment inference process to figure out which environment we're in. And finally, we added a dreaming feedback loop. So essentially, our agent dreams back past environments to ensure that it doesn't forget it. So we ran the unit test to see if it works, and we wanted to train our model, which we called Vase, on 3 data sets. First is a moving fashion MNIST. So it's fashion MNIST piece of clothing that moves around in a frame. We have standard static MNIST, and we have moving MNIST. So what happens is, first, the agent has 8 latent variables to use, and it allocates just 4 to represent the moving fashion MNIST. And so what we're plotting here is traversal 1 latent. So when we move this 1 latent, the object moves up, down. So essentially, it learned to represent the Y location. This is X. And 2 latents for the actual item of clothing. Now, when we move to MNIT, it automatically detected the shift. It logged down the previously learned latents and allocated the remaining 4 to now learn about the digit identity. And finally, when we move to moving MNIST, it's figured out that actually the movement part is shared with the moving fashion MNIST, and it's reused the XY latents from before and a few of the digit latents from the MNIST training session. And compare this to the VAE baseline, which basically uses its full capacity on the first dataset and then just rewrites it on every new dataset. So then we trained a classifier on top of this representation to try to classify the digits. And what's cool is when we learn about fashion MNIST clothing items, the performance of the classifier does not drop, even though when we start training on the other datasets. Essentially, we're not suffering from catastrophic forgetting. But the coolest part of this work is the semantic sharing that I mentioned to you. So we actually ran the exact setup that I used to motivate this, this model. We trained it both on the indoors DM lab dataset and the outdoors natural lab dataset. And then we presented the image from one environment and asked the model to imagine what it would look like if it were an equivalent scene in a different environment. And what we see here is semantically relevant sharing, where cacti in the natural lab are seen as equivalent to objects in the inside environment, and walls in the inside environment are seen as equivalent to the edge of the world in natural labyrinth. and again compare it to an entangled baseline where the reconstructions are based more on the high-level pixel similarities rather than deep semantic meaning. So now we have a really nice disentangled representation that we can learn in a lifelong fashion. But as I mentioned before, there is a lot of evidence coming from cognitive science that says that actually we want to have a hierarchical and compositional structure to our representations. What does this mean? So one way to motivate hierarchy is to think about the taxonomy of animals. So for example, if you think about birds, they'll have quite a few features in common, like they'll all have beaks and feathers. But if you go down the hierarchy to a class of penguins, then they'll have all the features that birds have in common plus more. So they'll have a lot more features. So we want our representations to share this sort of hierarchical structure. We also want our representations to be compositional so that we can recombine the building blocks in novel ways. For example, if I ask you now to imagine a red bird with no legs or wings that approaches the shape of a ball, I hope you imagine something like this, or any of those. But the key is all of these birds match the description. Hopefully you wouldn't have seen all of them before, so they're novel, and there is a lot of diversity. So how can we have the same? And also we want to learn from very few samples because this is what humans and animals do. So for this, we devised something we call SCAN, which we presented at HLAI this year. So it starts with a pre-trained BTVE that recovers the generative factors of the environment, but then we add an extra BTVE, which we call SCAN, and this one now takes words, so it takes symbols, like red suitcase, and tries to reconstruct. So it starts off with the same objective function as the BTVE, but now we want to ground the latent of the SCAN into the latents of the visual BTVE, and we add an extra KL term. So when we train the model, we give it a label, and then we show very few visual examples. So show a few red suitcases in different environments. And essentially, we want the SCAN model to become the prior over the BTVE latents. So after training this model, by showing just 5 examples for each concept, we can now give a new label to the model and ask it to imagine what it looks like. And so here we say white suitcase, and we can see that it generates diverse samples where the white suitcase is present. Or alternatively, we can give it an image and ask it to describe, and again, describes it using symbols at all the different levels of the hierarchy for this data set. And the cool thing is, it outperformed all the baselines, both in the accuracy and diversity of its samples, including Triple Elbow, which was developed concurrently, independently within the Kevin Murphy lab and presented at the same time as ours. But it also works on more complex and messy data sets like CelebA. If you ever worked with CelebA, you would know how the attributes are actually quite noisy. Some of them don't match the image. Some of them are very subjective, like attractiveness, and also they're binary, right? The attribute is either present or not. But what SCAN does, basically, it discards labels that are not informative, and for the ones that are informative, it learns a continuum. So now you can ask, imagine what faces look like with very pale skin or like not pale skin at all. You can also investigate what kind of biases there are in the dataset, because you can say, well, what do you understand attractive to mean after observing CelebA? And we see that there is huge bias towards young white females. So now we have a really cool representation, but are they actually useful for anything? So we did a very basic experiment, which we presented at CML last year. We designed a model called Darla, where we put an agent into a very simple room, which has 2 types of objects in it. We call it the seek avoid task, where one of the objects is always positively rewarded and one is negatively rewarded. In this case, cans are good and hats are bad. And we also have another pair where cakes are good and balloons are bad. We also have 2 room colors. And what we do is we train the reinforcement learning policy on these 3 combinations, and then we put the agent into this conjunction and ask, does it still understand that it should collect cans and avoid hats? It sounds easy because it has experienced all the objects and all the rooms, but actually it's not so straightforward. So this is your a generic vanilla reinforcement learning agent. It takes some frames in, it puts it through some sort of convolutional stack. It has an implicit representation, and then on top it has a policy network that actually outputs which action the agent should take. But normally there is no regularization on this representation, so it normally learns something quite unstructured. So we visualize this as some sort of entangled representations of objects and environments. So now when we present these, when we train the policy, it gets projected to some space here, and the policy learns what's good and what's bad. But when we move to the target domain, this conjunction that the agent has never seen before, it gets projected to a space in the implicit representation that actually the policy doesn't know about, and so it wonders what to do. However, when we try to put some structure in here and actually use a BTVE to pre-train the visual stack, we are able to factorize the environment from the objects. And now the policy learns a decision boundary that only depends on the objects and ignores environments. And essentially, we can project new conjunction into exactly the same structure that the policy was trained on, and so it still works. So we evaluated, so this is basically the DARL agent. It's a pre-trained BTVAE with a policy stack on top, and we tried 3 different reinforcement learning training algorithms. And we found that on this zero-shot transfer scenario, DARL outperformed all baselines by a big margin. And also the degree of how well it did in the transfer scenario was correlated with how disentangled its visual representations were. We also applied it to a more naturalistic domain. So we trained DARL to reach for an object in a Mujoko, with a Mujoko robotic arm in simulation, and then we tried to transfer it to reality. And this is a big problem in robotics, this seam to real transfer. And we found again that DARL outperformed all the baselines. So, to conclude my talk, I hope that I've given you some motivation and maybe persuaded you a bit to think about unsupervised representation learning, because I believe it's very crucial to reach anything approaching artificial general intelligence. Since unsupervised representation learning is such an unstructured problem, it's also very useful to look at the brain, because it's the only existing system we have that possesses intelligence. And finally, disentangled representations seem to be quite useful because of the compositionality properties that it has. And once we learn disentangled representations, we can learn more robust policies on top, and it's much easier to learn hierarchies and abstractions on top as well. But of course, there are many unanswered questions still. If we want to scale this up, we really need to get a better theoretical understanding of how our algorithms work and what disentangling is. In fact, there is actually no agreed upon definition of disentanglement in the field. And if we get this theoretical understanding, not only will we be able to scale up our algorithms, we should also be able to actually devise an unsupervised metric, which we can then start applying these algorithms to domains that we don't understand ourselves. And then hopefully, since we're starting off with inspiration from the brain and then validate our algorithms against the brain, hopefully we can use our algorithms to inform us how the biological intelligence works as well. So on this note, I would like to thank you for listening, and I would like to thank my colleagues in the team and all our wider collaborators within DeepMind.
And it's question time again. Thank you for your talk, Irina. Let's start with a question by Ed Pell from IBM. Gentleman in the middle there. Can your agent disassemble a chair and reassemble the parts? Can it understand objects as composed of objects?
We believe that understanding the objectness of the world and kind of part-whole decomposition is incredibly important. It's an active area of research. Currently, BTV out of the box does not necessarily do the object-part decomposition and wouldn't necessarily understand like what's a sheep, what's a flock of sheep, but we are working towards that.
Jan Sweeney, Nature Research, top left. How do you actually measure the accuracy or performance for the white armchair task?
Sorry.
How do you measure accuracy or performance for the white armchair task?
So that's a very good question. Currently, we only have supervised disentanglement metrics, which means that, in fact, to evaluate our training, we still need supervision labels, which kind of defeats the point of unsupervised representation learning. This is why I'm saying that we really need to understand what exactly do we mean by disentanglement so that we can measure it in an unsupervised way. So currently, the only way we have to evaluate our models is by visual inspection of latent traversals, which obviously wouldn't work for any domains where we as humans don't have an intuitive understanding what the generative factors are, or we can't just like immediately see through traversals what's happening.
Jaroslav Vitku from GoodAI. Middle there, white t-shirt. Have you considered some kind of active learning of the latent factors?
Again, a very good question, and something we're definitely thinking about. Currently, so for Darla, when we were pre-training the vision, we actually used a hand-coded exploration policy. It was almost random. We just tried to avoid walls. But of course, in any interesting environment, we actually want to kind of collect the good data distribution to learn good representations from. So again, it's an active area of research, figuring out how can we instill intrinsic motivation, curiosity, these kind of things into our agents.
Okay, I hope I assigned first and last name right. Fernando Germantorales Chorne from the M-Tank. Up there, orange t-shirt. How do you address the problem of a growing need for disentanglement as you generalize with more and more complex environments? So have you thought of growing the size of the latent space that might be limited in size to add more representations?
Yes, another brilliant question. All of these we are definitely thinking about. So as I mentioned, we do need to scale this up. Currently, we are limited by the optimization of variational autoencoders. We have made some progress into that with the Vase work, where now we can kind of continually train on many different data sets and keep adding the latents to the representation. But I think what is going to be important in the future is something to do with attention, because we don't, like even biological intelligence doesn't perceive the world in its wholeness, right? We have very small fovea and we saccade around and we perceive just small parts of the image at a time. And it also relates to active perception, where we might look at the world at like some basic scale, but then maybe we care about some level of detail and we might want to pay attention to maybe the leaves on the tree or like the sheep in the flock.
And final question for this round by Michael van Elk from FinApps, over there. Have you tried to apply these algorithms to other domains yet? Which area do you believe is most promising for it?
We are thinking about this. I think basically the problem right now is if we try applying it to other domains, we would not necessarily know how to evaluate our models. So this is why this unsupervised disentanglement metric is almost crucial to move, both to move to different domains and to scale up. We have started applying this to temporal data, so kind of videos, but of course it's just kind of extrapolating in time, but it's still a visual domain.
Okay, let's thank Irina again.